Hello everyone, Assalamualaikum. Now we are going to continue our lesson with Chapter 9, Bipolar Junction Devices. Previously, we have learned on PN junction, which makes the simplest device, that is diode. A PN junction is formed by having an N-type semiconductor and P-type semiconductor joined together side by side. By adding electrical connections or electrodes at the end of both N-type and P-type materials and connecting them to an external source, the PN junction becomes a diode. This figure shows the current voltage characteristics of a diode. We can see that the current increases only when the diode is biased with forward bias. However, we can also observe negative current being produced under strong reverse bias, which means at this state the breakdown happens. We have also discussed the band diagrams of PN junction and the representation of carrier flows and their currents that can explain the IV characteristics. Combining two PN junctions back to back will form a bipolar junction transistor, the device that we are going to learn from now. Thus, while applying the knowledge from PN junction, the objectives of today's lesson are to study and understand the basic of BJT structure and its band diagram. First, let's have some introduction on bipolar junction transistor or BJT. BJT is a discrete semiconductor device that has three terminals, or physically, three pins that can be connected to an external circuit. The three pins are known as emitter, base, and collector. The BJT operates based on the concept that when a small amount of current flows between base and collector, a larger current is generated and flow between collector and emitter. BJT can function as a switch in digital circuits and as an amplifier in analog circuits. It has two types based on the doping structure, which are PNP and NPN. For PNP structure, the emitter and collector are P-type semiconductor and the base is N-type. As for NPN, emitter and collector are N-type and base is P-type. There are three modes for operation of BJT: active, saturation, and cut-off modes. Under the active mode, BJT functions as amplifier where the output current is larger than the input. The saturation and cut-off modes are the modes where BJT acts as a switch. Under the saturation mode, the switch is on, and under cut-off, the switch is off. You can read the advantages and disadvantages of BJT in the lecture notes. Now let's talk about BJT structure. As mentioned in the previous slide, BJT has three terminals: emitter, base, and collector. Thus, the body can be divided into three regions: emitter region, base region, and collector region. Emitter region is usually highly doped so that it can emit or supply a lot of carriers to increase the device efficiency. Thus, for an NPN BJT, emitter is made of a degenerate N-type, denoted as N+, and for PNP, emitter is made of a degenerate P-type, denoted as P+. The base will be made of a material that is different from the emitter. So if the emitter is N, then the base is P. And if emitter is P, then the base is N. This will create the first PN junction in the BJT, which is the PN junction between the emitter and base. Usually, we denote this as the EB junction. Then the collector will have the same doping with emitter, so that is the second PN junction for the BJT, which is the collector base junction or CB junction. Collector is doped in lower concentration than the emitter. Shown here is the planar structure of BJT, which is typical in the 1970s, but since it is simple, thus we will use this to study further on the basic principles. The top view is shown here. We have the electrodes for all the three regions, denoted as E for emitter, B for base, and C for collector. From the cross-section, we can see that the E electrode is connected to the degenerate N+ region. This is the emitter region. B electrode is connected to a degenerate P+ region. But bear in mind that this P plus region is not exactly the base region, because we know theoretically base is not degenerately doped. We can see here that the P plus region is further connected to the thin P-type region. This thin P-type layer is the actual base region. The P plus region here is only to create a very low resistance contact between the semiconductor and the base metal contact. Next is the collector electrode. The collector electrode is connected to a degenerate N plus region, which in turn connected to a degenerate N plus buried layer. Again, bear in mind that the collector region is also a lightly doped semiconductor. So further looking into the structure, we can see that the N plus buried layer is connected to an N-type region labeled as N-well in the figure. This is the actual collector region of the BJT. Same as the P plus for the base, the N plus regions connected to the collector electrode is to create a low resistance path for the carriers to flow. So, the actual transistor mechanism of a BJT happens at this region. At this region, if further simplified, can be represented as this box model shown here, where we can have the emitter electrode connected to the degenerate N plus region, base electrode to the P-type region, and C connected to an N plus region, which is in turn connected to a lightly doped N-type region. The two PN junctions are here, a one-sided N plus P junction at the emitter base boundary, and a normal PN junction at the base collector boundary. Please remember that you will have to use different equations for calculations related to the EB and CB junction, because EB junction is a one-sided junction and CB junction is a normal PN junction. These are the circuit symbols for BJT. On the left is the NPN and on the right is the PNP BJT. The plus and minus signs shown here are the polarities of the bias that are needed to be applied in order for the BJT to operate in active mode. And both voltage and current calculation obey the Kirchhoff voltage and current law. We have mentioned that there are three operation modes for BJT: active, saturation, and cutoff. Under active mode, the BJT functions as an amplifier. To make the BJT operates in an active mode, the emitter base junction must be in forward bias and collector base junction in reverse bias. That means for an NPN BJT, for it to be in the active mode, the N-type emitter need to be connected to the negative and P-type base need to be connected to the positive, so that the EB junction is forward biased, and the collector need to be connected to the positive and the negative connected to the base so that the CB is reversely biased. Other operation modes with their respective biasing polarity are shown in this table. These figures show the direction of current flow in an active mode of a BJT. For an NPN BJT, the current flows from collector to emitter, and for the PNP BJT, the current flows from the emitter to the collector. There are three possible ways to connect a BJT in a circuit in which one terminal is being common to both input and output. We have common base, common emitter, and common collector. Among the three, common emitter is the most common configuration. We will talk further about common base and common emitter from now. So let's take a look into the two common circuit configurations. In common base configuration, the base is connected to ground, which is common to both input and output signal. Under this configuration, it has the voltage gain but no current gain. For common emitter configuration, emitter pin is connected to the ground, and for this configuration, it has both current and voltage gain. The current voltage characteristics of the BJT are shown here. The left is for NPN BJT, and the right figure shows the PNP BJT. The IV characteristics has three regions: active region, voltage saturation region, and cutoff. There is also differences in shape of IV characteristic for common base and common emitter configurations. For common base configuration, the in the NPN BJT, electrons are injected from emitter and passed through the thin base, then diffused to the collector. Thus, most of the emitter current contributes to the collector current, and we get that IC equals to alpha IE, of which alpha is the current gain for the common base configuration. Since there is a very small fraction of electrons recombines at the base, alpha will be less than 1, typically in the order of 0.99. For common emitter configuration, similarly, electrons are injected from the emitter and pass through the base and diffused to the collector. Small fraction of the electrons are injected to base and recombine and flow out of the base contact. Most of the electrons that pass through the base will be collected by the collector, and we get the relation between IC and IB is IC equals to beta IB, of which beta is the current gain for common emitter configuration. Beta is very large, typically in the order of hundreds. Since in the next subsection we will discuss on the current flow using the Venn diagram, thus we need to understand the Venn diagram. Further discussion on the BJT structure from now on onwards will be using this simplified box model of BJT and the assumptions written here. And we will only give the examples using NPN BJT. Thus, you need to understand the examples very well so that you can apply the knowledge for the PNP BJT. The assumptions that we have to make for NPN BJT are: the emitter is made of a degenerate N+ type, the base is a non-degenerate P type, and the collector is a non-degenerate N type. The doping concentration is the highest for the emitter, followed by the base, and the collector has the lowest doping concentration. The Venn diagram of the BJT at the equilibrium is the combination of equilibrium Venn diagram of a degenerate N-type semiconductor for the emitter region and a normal P-type and N-type semiconductors for the base and collector regions, respectively. Please remember that we have to keep the Fermi level constant all throughout the system. For the emitter region, since the doping is degenerated, thus we draw that the conduction band level EC is overlapping with the Fermi level to show that the doping level is extremely high. The two PN junctions that associates with the BJT operation are the emitter and base boundary, or we call EB junction, and at the collector and base boundary, or CB junction, as shown here. For the example, the most important operation mode that we will discuss further in the next subsection, which is the active mode. To draw the Venn diagram for the active mode, we will just have to combine the Venn diagram of the N+P junction under forward bias at the EB junction region and a reverse biased Venn diagram of a PN junction at the CB junction region. Please make sure that you know how to draw the Venn diagrams of other operation modes and also the Venn diagram for a PNP transistor at equilibrium and their respective operation modes. To summarize, BJT is a three-terminal device consisting of two PN junctions. The three terminals are called emitter, base, and collector. It has two most common circuit configurations, which are the common base and common emitter configuration, and the three most common operation modes, which are the active mode, saturation mode, and cutoff modes. Under active mode, BJT acts as an amplifier, and they act as a turned-on switch under saturation and off switch under the cutoff modes. The emitter region is made of a degenerately doped semiconductor, while base and collector are a non-degenerate semiconductors. The Venn diagrams are a combination of individual Venn diagrams of the respective regions and their related biasing types depending on the operation mode. And these are my references. Don't hesitate to ask questions if you don't understand at the WhatsApp or also at the FB page. Thank you.